So, welcome you all. So, in the last class, we have studied about three-phase half-wave rectifier circuits, and in this class, we are going to discuss about three-phase diode bridge rectifiers. Okay, so three-phase diode bridge rectifiers are commonly used for high power application because they have highest possible transformer utilization factor for a three-phase system. Because here since it is a bridge rectifier, in the both half cycles there will be output. Okay, and here we are using diode in this rectifiers. So this rectifiers will be a uncontrolled rectifier. It will be an uncontrolled rectifier, and the diodes are numbered in the order of sequence, and the conduction angle of each diode will be 2 pi by 3 or 120 degree. Conduction angle of each diode will be 2 pi by 3 or 120 degree, and here 6 diodes are used. In the case of half-wave rectifier, only 3 diodes were used in each 3 phases, but here we will be using 2 diodes in each phase. Okay, so total of 6 diodes will be there, and the sequence of diode numbering will be like this. In upper arm we will be having diode D1, D3, D5, and in lower arm we will be having diodes D4, D6 and D2. The primary of the transformer is connected in delta configuration, and the secondary of the transformer is connected in star or Y configuration. And you can see here in the phase A or in the line A, you can see 2 diodes are connected, D1 in upper arm and D4 in lower arm. And in phase B or line B, you can see here D3 is connected in upper arm and D6 is connected in lower arm. And in phase C, you can see here D5 in upper arm and D2 in lower arm. Okay, and also one more thing, in the case of bridge rectifier, three-phase bridge rectifier, 2 diodes will be on. In the case of half-wave rectifier, there were only 1 diodes were on in one cycle. Here 2 diodes will be on in one complete cycle. Suppose if D1 and D2 is turned on, the conduction path will be like this. I will show here. Suppose if D1 and D2 is turned on, means D1 means it is connected in this line A. So if D1 is turned on and D2 is turned on, so the conduction path will be like this. It will come like this. It will come like this. So this will be the conduction path if diode D1 and diode D2 is conducting. So you can see here across load we will be getting not phase voltage, we will be getting line to line voltage, because here one line is there C and another line is A. So we will be getting line to line voltage here. Okay, line to line voltage we will be getting here as output. But in the case of half wave rectifier, we got here phase voltage, but here we will be getting line voltage. So this line voltage means VAC line voltage will be here in the output side when diode D1 and D2 is conducting. When diode D1 and D2 is conducting, we will be getting line to line voltage VAC at the output. Okay. Now the same figure I have redrawn here. Okay. So you can see here in line A, 2 diodes are connected, right? One is D1 and another one is D4. D1 and D4, and in line B, D3 and D6 is connected, and in the line C, D5 and D2 is connected. D5 and D2 is connected. Okay, so you can see here one half wave rectifier is there, and here another half wave rectifier is there connected in opposite direction. So in the both the half cycle, in positive half cycle and in the negative half cycle, these diodes will be conducting. In positive half cycles, the diode D1, D3, D5 will be conducting, and in the negative half cycles, the diode D4, D6 and D2 will be conducting. Okay, so this full wave bridge rectifier will be working like two half wave rectifiers in each cycle. So in the positive half cycle, the diode D1, D3, D5 will be conducting, and the output waveform will be getting like this. Okay, like this we will be getting output waveform. Okay, for that phase, and during negative half cycle, the diode D4, D6 and D2 will be conducting, and we will be getting output voltage like this. Okay, and the average output voltage will be the combination of this both half cycles. And one more thing, in the case of half wave rectifier, we came to know that VDC means average output voltage in one cycle is 3 root 3 by 2 pi Vm, 3 root 3 by 2 pi Vm. So here in this positive half cycle, we will be getting average voltage 3 root 3 by 2 pi Vm, and in the negative half cycle, we will be getting average output voltage like minus 3 root 3 by 2 pi Vm. So here the average output voltage for this three-phase bridge rectifier, it will be like 3 root 3 2 pi Vm minus 3 root 3 by 2 pi Vm. So we will be getting average DC output voltage in case of three-phase diode bridge rectifier as 3 root 3 by pi Vm, 3 root 3 by pi Vm. So this is the average output voltage, average output voltage here. Okay, so this will be the average output voltage here, and the conduction I have already told, we will be getting output, we will be getting as line voltage, output will be getting line voltage. That is, if line A means if diode D1 and D2 is conducting, the path will be like this. If diode D1 and D2 is conducting, the path will be like this. Okay, so here the output voltage will be VAC. VAC means line voltage, right? VAC is the line voltage between line A and line C. Okay, and if D1 and D6 is conducting, if D1 and D6 is conducting, you can see here the path, current path will be like this. D1 and D6 is conducting, the current path will be like this. Okay, so here the output voltage will be VAB. Okay, now if D6 and D5 is conducting, the path will be like this. You can see here, if D6 and D5 is conducting, the path will be like this, and the output voltage will be VBC. So whenever the output is coming, we will be getting it as line voltage, but in the case of half wave rectifier, three phase half wave rectifier, we got output as phase voltage. So I have already told, in the case of 3-phase diode bridge rectifier, we will be getting output voltage as envelope of line voltages, okay, not the phase voltage. We will be getting output as envelope of line to line voltage, not phase voltage. So at any instant of time, two diodes will be on, already we have told. So line voltage will appear across the load, and the output voltage will be the envelope of line to line voltages. Output voltage will be the envelope of line to line voltages. Here you can see the three phase voltages you can see here. So here this is the first phase VA, and this is the second phase, which is 120-degree phase shift, which will be having 120-degree phase shift between VA. This is the second phase, and this is the third phase. Okay, so we'll be getting output voltage as envelope of line voltage, not the phase voltage. Okay, that we can see in a slide, that I am drawing the three line voltages. First one is VAB. Okay, this is VAB, not phase voltage. I am drawing the line voltage. VAB I have drawn. Now the second one is VBC, that is here. This is VBC, and the third one is VCA. Every voltage having 120-degree phase shift between each one, and the different in voltages VAB, VBC, VCA are drawn. Each will be having 120-degree phase difference between them. And now we will be drawing the 180-degree phase shift waveform of those three waves what we have drawn earlier. That is VAB is this one. From that 180-degree phase shift waveform also we will be drawing. 180-degree phase shift waveform means just opposite you have to draw, that is this one. So this will be VBA. Okay, VBA, red dotted line. This will be VBA, and VBC is this one, this yellow line. For that 180-degree phase shift means we will be getting VCB. This is VCB. Okay, now this green line is VCA, and the green dotted line will be VAC. Green dotted line is VAC. So 180-degree phase shift lines also we have drawn. Fine. Now you can see here, here which voltage is higher. This yellow dotted line means VBC. So yellow dotted line means VCB. So VCB will be higher here, and here red non-dotted line means VAB, and here green dotted line, green line means VCA. So green dotted line means VAC. Okay, now yellow line means VBC, and here VBA. VB means red non-dotted line is VAB. So this red dotted line will be VBA, and this will be green line means VCA. Okay, then so we will be getting output in 6 cycles, and you can see here VCB means which voltage is VCB. This is C and this is B. So VCB means you can see here from C it is coming. Okay, so diode D5 will be conducting. Now have to come to B, right? B means this 6. Okay, So our circuit will be, means our current path will be like this. Okay, so here you can see diode D5 and D6 is conducting, that is what is written here. Diode 5 and 6 will be conducting here. Okay, now next cycle you see here VAB is maximum. Okay, so VAB maximum means this is A, this is B. So you can see here diode D1 and diode D1 and D6, B means here. Okay, so current path will be like this. So diode D1 and diode D6 will be conducting, that is written here 6 and 1 VAB. Similarly that pattern repeats, and this each interval will be 60 degree. So total 60 into 6, that is 360 degree conduction. Each small interval will be 60 degree and total it will be 360 degree conduction. And the 180 degree out of phase line voltage waveforms are drawn because the current can flow either from phase A to phase B or from phase B to phase A. Means the current can flow from phase A to phase B and also from phase B to phase A. So because of that this 180 degree phase shift line also drawn, and the working of the rectifier can be understanding from looking at the envelope. And envelope, you can see envelope means that will be the envelope of line to line voltages, envelope of line to line voltages. And coming to the DC voltage calculation, VDC will be equal to, you can see here, if I am taking this as reference line, okay, this is reference line, and I have already told 6 intervals will be there. So and also I am taking this area only. Okay, so this is total 60 degree, half of this means 30 degree. So interval will be from 0 to 30 degree, that is 0 to pi by 6. And here we will be getting output voltage, that is line voltage. So line voltage will be equal to root 3 times phase voltage. So root 3 times Vm will be the maximum value here. So we will be getting 0 to pi by 6 root 3 Vm cos omega t d omega t. Okay, and here I have taken this part only for area. So this total area means we have to multiply it into 2, and total cycle means it will be 2 pi, so 1 by 2 pi. And you can see like this 6 intervals will be there, 1 2 3 4 5 6 intervals will be there. So we have to multiply it with 6. Okay, so solving we will be getting VDC, which will be equal to 1.654 Vm. And similarly Vrms also same equation, you have to take the square of this part, this term. Okay, and overall you have to take square root. So Vrms will be equal to 1.6554 Vm, and VAC also will be getting from this equation. And here I have already told output will be the envelope of line voltages. So we have to convert that phase voltage into line voltage. So you have to multiply it with root 3, and there will be 6 intervals. In that diodes will be conducting like this: 5 6 6 1 1 2 2 3 3 4 and 4 5. And each pair of switches will be conducting for 60 degree. This small interval will be 60 degree. Okay, this small interval will be 60 degree. And the current waveform is shown here. Okay, the current waveform is shown here, that line current only. Line current you can see here. Here it is VAB. VAB means VA minus VB. Okay, VA minus VB means this current through line A. Line A means it is positive. So since it is a resistive load, current waveform also will be similar to that of voltage waveform. So it will be like this. Okay, and here you can see VAC. VAC means VA minus VC. So there also current is positive. Okay, so we will be getting like this. So there you can see VBA. VBA means VB minus VA. So here the current is following in opposite path. So it can be represented like this, with maximum line current voltage minus root 3 Vm by R. And here VCA. VCA means VC minus VA. So here also current is flowing in opposite direction. So it can represent minus root 3 Vm by R. So average line current here it will be 0, because you can see here when output we are getting VAB and VAC, we are getting positive currents, and when output we are getting VBA and VCA, we are getting opposite current. So average output line current here it will be 0. Okay, and coming to the diode current, you can see here, if I am taking this as reference line, and I can write ID will be equal to ID RMS will be equal to diode will be, means this is one part, this is another part. This diode, you can see diode 1 will be conducting for this 60 degree and this 60 degree. Okay, so total 120 degree this diode is conducting. So 1 2 3 4 part will be there, so it should be multiplied by 4 by 2 pi. The interval will be, this total is 60, so this will be half of 60, that is 30 degree. So 0 to pi by 6 Im square cos square omega t d omega t. Solving we will be getting 0.5518 Im, and that is diode RMS current. Now coming to the line current. Line current means, you can see here, this is the line current waveform IA. Okay, so here you can see, if I am taking this as reference line, you can see how many part is there, 1 2 3 4 5 6 7 8. So it will be 8 divided by 2 pi, and the limit will be, this is 60 degree, so half of that it will be 30 degree. So 0 to pi by 6 Im square cos square omega t d omega t. Finally solving we will be getting IA RMS, that is line current RMS, which will be equal to 0.7804 Im. So here the diode D1, you can see diode D1 is conducting in these two intervals, that is 16 to 2 120 degrees, and one line you can see VA is conducting in VAB, VAC, VBA and VCA. Okay, that is 4 into 60 or 120 into 2 240 degree, line conducting for 240 degrees, and one diode will be conducting for 120 degrees here. Okay, and coming to the calculation, we have already got VDC, VRMS, IDC, IRMS. Okay, from that we will be getting PDC and PAC, and the rectification efficiency here we will be getting around 99.83%, and form factor 100.08%, and the ripple factor here it will be only 4%. In the output we will be getting only 4% as ripple. So this is all about 3-phase bridge diode rectifiers. With this I am concluding this topic. Thank you.